So I left everybody a hint here at the end of our last video, and I mentioned that it seems interesting that whenever we have a bijection between two sets, let's say a set A and a set B, whatever that bijection is, okay, we notice that the sets are pretty much the same size. So we got into talking about sets without talking about the size of a set. And this topic is what drove the mathematician Cantor practically insane. Because when we talk about the size of sets, remember, sets can be broken up into two major categories. Either they are finite, where, in other words, we can list out each element in the set explicitly and have a definitive end in that listing, or the set is non-finite, and in which case there is no definitive end. Now, in terms of finite, these are easy things to think about when we talk about the size of a set. When we talk about finite, we just simply mean, how many elements, counting-wise, are there? So if I were to write, let's say, this, how many elements are in this set? If you remember, this set is denoted by here, and this is what we called the empty set. And given that there's nothing in the set, we can really just denote that as 0. On the other hand, if I have this set, how many elements are in here? Well, obviously there's 1. What about this set? Obviously there's 2, and so on and so forth. So for finite sets, understanding how many things or how much stuff is in are in these sets is frankly just easy. We just count, right? And that count, that how many, is what we refer to as the cardinality of the set. Usually, when given any set A, when we have brackets, lines, kind of like how, there's the absolute value around the number, if you remember that notation from algebra, right? This notation in set theory is intended to represent the size of a set. So when we talk about the size of a set, this is just simply how many elements are in that set. Now, in the case of finite, this is very easy, as we mentioned, right? If, for example, A is equal to T1, 5, 6, 8, B, and A, then there's 1, 2, 3, 4, 5, 6. And so the size of A is therefore 6. So with finite sets, it's very easy to find the cardinality. And as we had mentioned, if we have two sets, let's suppose we have another set, B, T2, 8, 7, A, C, and let's say, I don't know, a weird looking L. Then the cardinality of B is also 6. Notice that we can put each of these sets in a bijection with each other. That is, we can uniquely assign or uniquely map elements in set A to elements in set B. So at least in the case of finite sets, we know we have an interesting hypothesis here, which is that if A and B can be put into a bijection. That is, put more technically, if there exists a function f between a and b, or between b and a, doesn't matter, because if there's a bijection between a and b, there has to be a bijection between b and a. Think about that one. Then the cardinality of a must be equal to the cardinality of b. Now, what drove Cantor insane is the following idea. Now, if we have a set A, we have what's called the power set of A. The power set of A comprises of all of the subsets of A. So this is the collection of all sets B such that B is a subset of A. So for example, if A is the set 1, 2, okay, we have a few subsets. The power set of A would therefore be the empty set. The empty set is always a subset of every set. The set containing 1, the set containing 2, and the whole set itself, which is 1, 2, or put simply A. And that's what we refer to as the power set. But notice, interestingly enough, that the cardinality of A is not equal to the cardinality of the power set of A. And interestingly enough, the cardinality of A appears to be less than the cardinality of the power set of A. So we have some interesting things here that we can think about. Let's go to the case of the non-finite. And we're going to talk a little bit more about this in the next part of lecture 1. In the case of non-finite, we have two types of sets. We have sets that are what we refer to as countable, and we have sets that we refer to as non-countable. Let's consider a basic example. Let's consider the natural numbers. 0, 1, 2. Some mathematicians argue about 0 being in. I'm going to put 0 in here, okay? So on and so forth. This goes out to infinity. And so we might hypothesize that the cardinality of the natural numbers is infinity, right? Here's an interesting question that I want you to think about. We mentioned earlier that the cardinality of a set appears to be less than the cardinality of the power set of that set. Does that hold true in the case of the natural numbers? That is, the cardinality of the natural numbers, if we take the power set of that, right? If we take the power set of that, is the power set of, sorry, had a small mistake there. There we go. Is the cardinality of the power set bigger than the cardinality of the natural numbers? Now, either answer gives us some pretty interesting things to think about. If this is true, what that tells us then is that there's more than one infinity. If this is not true, then what this tells us is, in a very weird way, that some weird things happen at infinity. We tend to think that if we have an infinite number of things and we append something to it, is it bigger than infinity? That is infinity really the biggest thing that we can think of size-wise? Answers to these questions lie in the next subsection or next section of this lecture. And you are going to be interestingly enough, confused, but hopefully curious about some of the topics we're about to discuss, because one thing that I can rest assured confirm to you is that this is actually not true. And the reason is because there's not just one infinity. There's actually a lot of different infinities. And that sounds weird, but it will become hopefully a little bit more clear to you. One thing I can prove, I don't want to say prove, but one thing that I will state here is that what also holds for non-finite sets is that if there is a bijection between A and B, regardless of whether A and B are finite or non-finite, needs to be equal to the cardinality of B. So we're going to use this little fact here. In other words, to prove or show that two collections have the same amount of stuff in it, we need to find a bijection between them. If we can show that a bijection does not exist between them, then we have shown effectively that they are not the same size, or what we think of as size, and therefore they must be different sizes. Keep that thought in mind as we progress on to the next section of our lecture.